This video is part of an online course on algebra and will be about basic set theory. For the first few years of your mathematical journey, almost every object that you encounter would be a set. Therefore, set theory is the ideal starting point for this course. We begin with the first definition of this course, the definition of a set. A set is nothing but a collection of objects. There are two key words in this definition. The first is the word collection, the second is the word object. This definition is not really a definition. A definition is supposed to define a concept in terms of concepts that are already being defined. The issue is this is the starting point of mathematics. You have no further simpler objects to define sets in terms of. We have to begin our theory somewhere. So what we are going to do is we will take for granted that you understand intuitively what a set is. We use this notion of sets every time we talk about a bunch of grapes or a herd of cows. Mathematical sets are not that different, except the objects that we consider in our mathematical sets are just sets themselves. They are other sets. It's sets all the way down. So in this course, the objects of a set will always be other sets. The word collection will be left undefined. In the first part of the course, we will see what operations we can do on sets that do not land us in trouble. Briefly, in a future video, we will see what can go wrong if we take this naive approach to set theory. The famous Barber paradox will come into play. But we have to start our theory somewhere. So we are going to start with sets. If you are not satisfied with this non-rigorous naive approach, you can study the book Naive Set Theory by Paul Halmos. This book, even though the word naive is there in the title, is not that naive and it's quite rigorous. You can study that book if you want a formal axiomatic treatment of set theory. But we will not engage in axiomatics for set theory in this course, but rather we will take a completely naive approach. Nevertheless, if you are careful about what you do with sets, you are unlikely to land in much trouble. As I said, the objects of sets are going to be other sets. The objects of sets are called its elements or members. We will use both these words. You will notice that in mathematics, there will be several words to denote the same thing. This is often to break monotony and also for the reason that the genesis of mathematical objects came from different countries. So the original term might have been in French, which when translated becomes something in English. So you will have multiple words for the same concept. This is something that you should get used to. Now, all the objects that we are going to consider, including the elements of sets themselves, are other sets. But for reasons of psychology and pedagogy, as well as efficiency, we will always denote the main sets we are considering by capital letters A, B, C, S, etc. and denote the constituent elements by little letters X, Y, Z, etc. Note, this is not really a definition or a concept that I want you to understand. This is mainly just a convention that I will mostly follow to make your life and my life easy, right? So in this course, I will never write silly things like A is an element of little x. Such things I will not engage in. Okay. Now, so I've already used the word A is an element of. Let me formalize that. We will use the notation X is an element of A to be read as X is an element of A to denote membership. The symbol for that is this sort of epsilon-like thing, but sort of more straightened off. It's not really a fancy epsilon. Usually in Greek, you write epsilon something like this. Okay, so always read this as X is an element of A. This denotes membership. That means one of the constituent objects in the set A is the element X. And non-membership is denoted by almost the same symbol. X is not an element of A, or read X is not a member of A, by just writing that epsilon and striking it out. I'm sure you're familiar with this notation. This is just a brief recap. So, summary, you should think of sets as a bag. Within that bag, paradoxically, there are other bags. Within those bags, there are further other bags because every element of a set is going to be another set. How do you describe sets? Well, I'm sure you're familiar with this. The simplest way to describe a set is by merely listing out its element. So consider, for instance, the set A colon equal to 1, 2, 3. So you must be wondering, why did I put this colon equal to? So I'm going to be brief and explain the role of equality in this course. Throughout this course, equality is the same as logical identity. That means whenever you say something equals something else, what you really mean is the object on the left hand side is the same as the object on the right hand side. So why the presence of this colon here? What this colon denotes is the object on the left hand side up until now does not exist. I am invoking or I am bringing into existence the object A by this piece of code, if you can think of it that way. I am saying I'm creating a new object. The name of that object is A, and the value of that object is the set 1, 2, 3. So this notation means I'm bringing the name into play, the name being A and the right hand side being the set 1, 2, 3. So henceforth, the set A is always the set 1, 2, 3. In mathematics, as much as possible, we will not reassign the value of the variables that we are introducing. This might sound confusing. So if you are sufficiently confused, let me confuse you even further. If you think about this carefully, what is on the right hand side is also a bunch of names. For instance, this symbol 1 is a name. That name denotes the abstract entity, the number 1. So I hope now you are thoroughly confused, but do not worry. This is just a matter of convention. Just always think of colon equal to as bringing an object into existence, and just the ordinary equal to, read it as is same as or is logically identical. Okay. Before we proceed with what is to follow, maybe for as a test of your understanding, you can revisit one of the famous identities you must have learnt in 7th standard or 8th standard, which says a plus b the whole squared is a squared plus b squared plus 2ab. I'm sure you know this identity. Is this identity a logical identity? That is the left hand side same as the right hand side, or is the left hand side by definition equal to the right hand side? Think about this and you will have a better understanding of the difference between colon equal to and just plain equal to. If you are not able to understand this discussion about equality, do not worry, it will become second nature to you as you proceed in your mathematical journey. Coming back to our sets. A set is determined entirely by its elements. That means two sets are equal if and only if they consist of exactly the same elements. So the sets 1, 2, 3, 2, 1, 3 and 3, 1, 2 and several others are one and the same set. They are just different names for the exact same set. Furthermore, in sets, repetitions do not matter. You can put the number 1 as many times as you want and this name will still denote the set 1, 2, 3. Okay? So the set 1, 1, 2, 2, 3 is same as the set 1, 2, 3. As simple examples, you can now see that the set A has the number 1 as an element but does not have the number 4 as an element. equality of sets. As I mentioned, two sets A and B are equal if and only if they have exactly the same elements. In other words, in order to show that A equals B, no colon, we have to show that if X is an element of A, then X is also an element of B. Incidentally, this is the definition of A subset B, read as A is a subset of B. We also sometimes write B superset of A. Okay, so in other courses, you might have seen the term, the symbols A subset of B like this. You might have encountered this notation. Sometimes we will use this notation in this course also. A subset of B and the subset notation, we will use both these symbols interchangeably. Both mean the same thing. In some textbooks, this has a different meaning. This means A is a proper subset of B in some textbooks, but the vast majority of mathematical authors do not think of these two symbols as different, and we will also not think of them as different. Sometimes I will use this, sometimes I will use this. Okay? So A subset of B and B superset of A are the same thing, and this happens whenever X is an element of A, X is an element of B. We say A is a proper subset of B if A is a subset of B, but A is not equal to B. I have intentionally written A subset of B with the notation where there is no line here. Okay. To denote this, in this course, we will use this symbol. This is sort of universal. Authors might disagree whether this is proper subset or just subset, but everyone agrees that this means proper subset. Okay. And we will write A subset with a cross to mean that A is not a subset of B. When does this happen? When there is at least one element in A that is not in B. So if your set theory is rusty, or if this is the first time you're actually encountering this concept, maybe it's a good idea to pause the video and think about why this is the meaning of A is not a subset of B. Incidentally, some more notation. You notice this phrase, if and only if. Well, this phrase is going to occur so much in mathematics, and mathematicians being the lazy creatures, we have invented a special notation for this. We will abbreviate if and only if as IFF. So if you see this word IFF, it's not a dictionary word, it's a shortcut for if and only if. Also note, this is just for your historical knowledge, this notation was also introduced by Paul Halmos. Remember the guy I was talking about who wrote a book on set theory, entitled it Naive Set Theory, but there's nothing naive about that book. This notation was popularized by the mathematician John Kelly. Okay. Now, that is just one. How to show that two sets A and B are equal, you have to show that they have exactly the same elements. So you have to show that if X is an element of A, then X is an element of B, and you'll have to show the converse as well. So you have to show that if X is an element of B, then X is also an element of A. In other words, you have to show B is subset of A. So to show that two sets A and B are equal, you have to show that A is a subset of B and B is a subset of A. I'm sure you have done this several times in your life before in high school. Describing complicated sets. Well, the method of description of just putting some elements inside flower braces works nice and handy when there are just 5 or 6 elements in the set. To describe more complicated sets, that method simply doesn't work. So you use the next form, or the more general form, that is describing sets in terms of properties. So this is the general form. You define the set B to be the set of all elements X in A such that some property P of X is satisfied by X. That is, you collect together those elements of A which happen to satisfy this property. In the next video on basic logic, we will see what properties are, and at that point this will become clear. But you have definitely seen such things. For instance, you must have seen something like X in the natural numbers such that X equals 2m, m also in the natural numbers. What is this set describing? This just think about it. I'm sure you know what this set is describing. So, how do you read this? The set B comprises those elements of the set A that satisfy the property B. I will give some more examples to make sure that you understand what is going on. The first example we have already seen, denoting the set of natural numbers excluding 0 by n. We can define the set of even numbers by x in n, x equal to 2m for some n, m in n. The singleton set 3, the set within flower braces just one element, the element 3, is the set that contains the number 3 and is a set with just one element. Such sets are called singleton sets. Note that the set with the single element 3 is very different from the number 3. Well, 3 is an element of the set that consists of the element 3, right? So 3 is a member of the set with 3, but the set with 3 is not the same as 3. So again, this might seem very confusing. It will become second nature to you with practice. You can also define the singleton set 3 in a more complicated way, which I will come to in a moment. One thing you should be aware of, there is a way to construct natural numbers starting from basic set theory, and in one such construction, each natural number will be a set, and in that popular construction, 2 will be an element of 3, right? So that is really interesting. You can construct the natural numbers in such a way such that the natural number 2 is an element of the natural number 3. Now, let me describe the set singleton 3 in a much more complicated way. X in the natural numbers such that x squared minus 9 equal to 0. Remember, the natural numbers do not include the negative numbers. Those are called integers. So it is precisely those solutions of the equation x squared minus 9, and the only natural number solution for x squared minus 9 equal to 0 is the element 3. So this is the same singleton set 3 described in a much more complicated way. Now you might think I'm insane or a lunatic for defining the singleton set 3 this way, but let me tell you that one of the most famous open problems in all of mathematics, called the Riemann hypothesis, involves showing that a particular set is a singleton set, and that set's definition is not substantially different from the definition of the singleton set 3 that we see here. Now let me introduce notation for some of the famous sets that you will encounter in this course. These sets are famous outside of this course as well. I'm sure you have seen these sets before. The set n, denoted like this is the blackboard n. It's called the blackboard n, is a set of natural numbers, and in this course the natural numbers will not have the number 0. Then you have the integers, which is written blackboard z. I will write it like this, z with another line, slanting line. The set of rational numbers is the blackboard q, which I will just write it like this. The set of real numbers is the blackboard r, which I will write r with another line. And the complex numbers are the easiest to write down. I will write it like this, C. So these are the most famous sets, and they are famous because much of algebra is going to be relying on these sets. The subject of number theory, this set n and z, and sometimes even Q are the main objects of study. Surprisingly, the set C comes into play even when you're studying number theory. But that's the topic for another course. We now come to the empty set. Remember, I said that one popular construction of the natural numbers is in terms of set theory. Well, let's think about it. Our pseudo definition of sets is said the following essentially: a set is nothing but a collection of elements, where the elements themselves are other sets. Now, if you don't want to get trapped in an infinite regress, this process of set consisting of elements with our other sets, which in turn consists of other elements, must end somewhere. And it ends in many constructions, it ends with the empty set. So, if you were to be brave enough and at this stage study the axiomatic set theory from the book Halmos, you will notice that the axioms of set theory, popularly called the Zermelo-Fraenkel axioms, the existence of the empty set is taken as an axiom, right? So what is the empty set? The empty set is a set that comprises no elements at all. It is the bottom in our hierarchy of sets. Now, because the set phi, which is this is the symbol I will use for the empty set, red phi, it's a sort of like a digital phi, if I might be permitted to say that. This set has no elements, and for that reason, this set phi, the empty set, is a subset of any set A irrespective of what that set is. Why is that true? Well, let's think about it. How can it be false that phi is a subset of A? How can this statement be false? Well, if you think about it, the only way a set is not a subset of another set is if this set, the empty set, had some element X which is not there in the set A. But by definition, the set phi, the empty set, has no elements. Therefore, the empty set is a subset of every single set. I am giving the proof of a seemingly trivial fact now because there are some things to understand in this proof which relies on the notion of implication, and that will be made clear in the next video on basic logic. Now that you have seen that the empty set is a subset of every set, I suggest that you work out this next exercise that will help you understand the difference between being a member of, or is an element of, is a subset of, and the meaning of the empty set. The empty set can be an element of other sets, even though the empty set is a subset of every other set and the empty set itself has no elements, it can be the element of other sets. For instance, just consider the set A, which is by definition the set that consists of the empty set, and the second element of this set is the set that contains the empty set. Okay, this is actually quite a complicated set. So what I suggest you do is that you check that all the properties I have written down here are correct. And I am a tricky person, one of them might be wrong. So just make sure that you understand whether everything is correct and you know why everything is correct. The empty set is an element of A. The empty set is a subset of A. The set with empty set is an element of A. The set with empty set is a subset of A. And finally, the set with empty set is also a subset of A. Please check that all of these statements are true. This is a course on algebra and you have just watched the video on basic set theory.